The stuff that I'll tell you about is stuff that has started around 99 or 2000. I'll try to give you an overview, but really to my mind, from my perspective, the starting point for this work is really in the 2 years I spent at Princeton, so around 1996. And I remember very well those times. Then I was heading towards something which you might call microlocal analysis, maybe some work in unique continuation and so on. But Sergiu did his best to persuade me that I should be working on some real problems. And his idea of real problems was nonlinear wave equations, and at the time we spent quite a bit of time talking about one or another problem having to do with nonlinear wave equations, especially problems having to do with Maxwell-Klein-Gordon and Young-Mills, which, as you see, are coming back here. The stuff that I'll tell you about, we didn't have much of an idea what to do then, but the questions we were looking at that at the time was just to understand in a better way the local well-posedness theory and to bring it maybe closer to the critical Sobolev space. And that was the time when that was after Sergiu and Matei had introduced the XSB spaces in the study of nonlinear wave equations. But at the time when we were realizing that XSB spaces are not going to tell the entire story, and maybe the bilinear aspects of the theory were getting preeminence, looking at bilinear Strickhardt estimates, looking at other sort of bilinear interactions in this geometric wave equations, and this ended up playing a preeminent role later on. If you're looking for anybody to blame that I'm interested in nonlinear wave equations, this is Sergiu. He's sitting right there. But also later on in the work that I'll tell you about is with collaborators, and one common characteristic of all of these collaborators is they were all either Sergiu's graduate students or Sergiu's postdocs. So you can see his influence in this work in multiple ways. All right. Now, just by looking at this first slide, you might also tell that there is some considerable overlapping, in effect, between my talk and Joachim's talk. Our sort of agreement was that Joachim would emphasize more the soliton bit, and I will tell you more about the scattering part, if you wish, of the problem. So the questions that I will address concerning these three geometric wave equations are global well-posedness and scattering, and I want to look at the critical Sobolev space, and then I'll emphasize the energy critical dimension, and that's special because that's where it makes a lot of sense to talk about the large data problem. So I'll go fairly quickly through my first three slides where I introduce these two equations, which you also saw in the previous talk. So the wave map equation, this is a geometric wave equation where you're looking at maps which take value into a Riemannian manifold. It has a Lagrangian structure. If you look at the equation written in local coordinates, it looks like a semi-linear wave equation with a quadratic nonlinearity. This is the nonlinearity that, as Igor described earlier in the conference, has this nice structure, null form. You can also write this equation in a very short way, in a covariant formulation, where this, well, see here the derivatives of phi belong to the tangent space of the manifold, and so you can talk about the pullback of the covariant derivative on the manifold, and that's what this is here. You have a conserved energy And corresponding to this problem, like Joachim explained, you have a nice scaling and you have a critical Sobolev space. And with respect to the critical Sobolev space, if you compare this with the energy, you have the energy critical dimension n is equal to 2. And so I will tell you about problems in dimension 2 and in higher dimension. Then the Maxwell-Klein-Gordon equation. And here your variables are a Maxwell field and a complex field with the corresponding covariant differentiation induced by the Maxwell field. You have the Lagrangian with the two components, the one that comes from the wave equation and the one that comes from the Maxwell field. Either of these two Lagrangians taken separately would lead to linear equations, but when you couple them together, you get a nonlinear coupled evolution for A and phi. You can see if you want invariant way of writing the equation in here, and this involves the curvature of the Maxwell field, the electromagnetic tensor, and that's coupled on the right with a contribution coming from the scalar phi as a source. And then for the scalar field phi, you have a covariant wave equation. One important feature of this equation is that it has a gauge invariance. And this corresponds to the linear gauge invariance of the Maxwell field. And from a mathematical perspective, once you have a gauge invariance, you know that if you want to develop a nice PDE theory for this problem, you need to be fixing the gauge somehow, and so that will be one of the issues I will touch during my talk. And my third equation will be the Yang-Mills equation, where you're looking at connection valued one forms, which take values in a semi-simple Lie algebra. The difference compared to the previous Maxwell example is that this is a non-commutative theory. In particular, you see this in the formula for the curvature tensor. And you have the Lagrange action functional, which is similar to the Maxwell one. You can also write these equations in covariant form. And finally, you have the same gauge. Well, you have a gauge invariance, which looks a little bit like the Maxwell one, but it's this time, if you want, a nonlinear gauge invariance. And here, O represents functions which take values in the corresponding Lie group. You also have a nice conserved energy and the same kind of critical Sobolev space as for the Maxwell-Klein-Gordon equation. Now, maybe one thing that's not apparent in my discussion so far is that there you have a notion of gauge freedom for Maxwell-Klein-Gordon equation and a notion of gauge freedom for Yang-Mills equation. But for the wave equation, for the wave map equation, it would look like there is no gauge freedom. However, you can indirectly come up with the notion of gauge freedom for wave maps, and you can do this either in a more naive way by saying, well, my gauge freedom is really my choice of coordinates on the manifold M. But maybe in a better way, you can think of the gauge freedom in here better as a choice of an orthonormal frame in the tangent space to the manifold M, which plays a prominent role in the analysis later on. So you can think of all of these problems as gauged nonlinear wave equations, and this is critical for the entire theory. All right, so in terms of the gauge freedom, I wrote here the commutative version of the gauge freedom for the Maxwell-Klein-Gordon, and then the non-commutative version for the Yang-Mills equation. And the idea of the goal of choosing a gauge is to simplify as much as possible your analysis of the equation. And if you think about all the things you'd like to achieve with the gauge fixing, you'd like to make your equation look like a hyperbolic equation, number one. Number two, that was understood a little bit later, is that you want this gauge choice to capture the null structure of these equations, to make them look like nonlinear wave equations with which satisfy a null condition. And finally, you would like, in as much as possible, your gauge choice to work not only for small data, but also you'd like it to work for large data. And maybe this is not apparent at first, but these three requirements are really conflicting requirements, and we don't know of any single gauge that would fulfill all of these three goals. And because of this reason, we have a number of gauge choices, and the gauge that you end up choosing will depend on your specific problem and will depend on your specific objectives. So one gauge is the Lorentz gauge, which is, if you want, the single covariant gauge in all this story. This has the advantage that preserves hyperbolicity, but kind of fails for the other two goals. Temporal goals gauge has similar features, if you want, as the Lorentz gauge, also preserves hyperbolicity, but gives you a little bit more about the null structure of the equation. The Coulomb gauge is the one that is best in terms of the null structure of the equations, though as you'll see in a moment, sometimes fails to be globally defined. And so these are the three classical gauges, if you want. And finally, the caloric gauge, which I did not define explicitly in this talk, has to do with solving an additional covariant heat flow and then pulling back your, and this covariant heat flow, you expect it to converge to a steady state at infinity, and then that steady state at infinity, you pull it back along the heat flow, and that would give you a choice of gauge at the initial parabolic time. So you might say this is the most complicated one, but it's also the most robust one, and this will also play a role in my story. This was a gauge which was introduced by Terry Tao in our study of dispersive equations, and also not only in this problem, but also works well, as we've seen in the study of Schrödinger maps, which I will not touch during this talk. Okay. When you look at, so I promised I'll tell you about the small data problem, and then I'll tell you about the large data problem. When you look at a small data problem, you have essentially, when you have a semi-linear wave equation, your first naive choice is to try to think of your semi-linear equation in a perturbative fashion, where the nonlinearity, you want to add this as a perturbation on top of the linear wave flow. And the common feature of these three problems that I'm telling you about is that this does not work. If you look at this, either of these three problems in the scale invariant Sobolev space, your nonlinearity will never be perturbative. And instead, what the best thing you can do in terms of thinking of the nonlinearity as perturbative is you can peel off, if you want, a bulk of the nonlinearity, the green part that I put on the right. Think of this as perturbative, but there will always be some part of the nonlinearity which you think of as non-perturbative. But it has a redeeming property, namely that this, if you want, non-perturbative part of the nonlinearity arises in this equation in the linear part of the equation. So here K represents a dyadic Littlewood-Paley index, and so what you see in this equation is a perturbation given by the green term of a linear evolution of the dyadic part at frequency to the power k, that's phi k, on a background that depends on the lower frequencies of the solution phi. All right, so it's natural that when you try to understand such an equation, you have these two obstacles you're trying to understand. One, to understand what is the perturbative part and how you can estimate the perturbative part. And the second, you want to understand this paradifferential part of the equation, and maybe understand this in a way that's not very dissimilar to the constant coefficient wave equation, but definitely treating this term in here non-perturbatively. So these are the two key difficulties. First, you want to have some good function spaces for the perturbative part of the equation, and then you want a nice parametrics construction for this linear paradifferential problem. And of course, you want these two choices that you make compatible. And so I'll tell you a little bit about each of these two items, about the choice of the function spaces, and then about the paradifferential part of the equation. So when you look at the function spaces, you want to have, as always, two nice properties. One, a linear mapping property. So S will denote here the space for the solutions, N would denote the space for the inhomogeneous part of the equation. So you want a linear property in here, and then a nonlinear mapping property where you take the nonlinearity, or at least the perturbative part of the nonlinearity, and you want to show that this satisfies good estimates. And there was a long story about how one can best construct these function spaces. And of course, the starting point of this story was to use Strickard's type norms. This has worked well in many problems, but not so well in this geometric wave equations. And the reason why that is the case is because the Strickard's norms do not tell you very much about in terms of the null structure. And this difficulty with the null structure was very nicely addressed in the work of Sergiu and Matei by introducing the XSB type spaces for the wave equations, and by looking at bilinear estimates in the XSB type spaces. Now, the trouble with the XSB type spaces is that they worked very well in understanding problems above the critical Sobolev norm, but in order to work with critical Sobolev norms, and in other words, in order to also touch the global aspects of the problems, you would want to have spaces which have good scale invariance properties. And this is notoriously missing from the XSB spaces. And so as a sort of more robust replacement for the XSB spaces, we have at this point two types of spaces. One are the U2, UP, if you want, and VP spaces. These are, if you want, direct scale invariant replacements of the X1 half spaces, which don't have good scaling properties. And then the null frame spaces, and the null frame spaces are, and I'm not going to attempt to describe them, but they combine the Strickard's properties of solutions to the wave equation with multi-scale frequency localizations. These are adapted to the null cone, and you saw some nice pictures of that, especially during Bourgain's talk. So it's exactly the same kind of localization, except that you have to do this simultaneously at all possible scales. And so these two kinds of spaces emerged during my initial work on wave maps equation, and there is a bit of a story behind that, which Sergiu knows very well because he was the editor in charge of this. My first paper on two-dimensional wave maps equations, that's where this U2 and V spaces were introduced to address this issue of finding good function spaces. And maybe about half a year after I submitted the paper to Sergiu, somebody else, a graduate student at the time, Kenji Nakanishi, he found a mistake in my paper. Very subtle mistake. If you want, it was the kind of log kind of mistake. So I thought, oh, this is not a big deal, I'll fix it. That's at first. After a week, I thought, well, I should be able to fix it. And maybe after a month, I thought maybe I should better find a different way to solve the problem. And so the outcome of that was this null frame spaces, which increased the length of the paper by a factor of 4. But which did solve the problem. If you want, the moral of this is if you make a mistake, don't give up. Instead, get to work and fix it. And if you are not able to fix it directly, maybe something else equally interesting will come up. So in any case, this U2 and V2 spaces died at the time, but they came back later in work that I did with Herbert Koch on completely unrelated problems, and in the meantime have turned out to be very useful, so I thought I should mention them here. So that much in terms of these function spaces. Now, as I said, these are function spaces that are introducing connections to the wave map equation, and there were further refinements of these spaces, some due to Terry Tao, also Joachim Krieger did some work on improving this. And so one should not think of these spaces as something very rigid, should think of them more as a philosophy that you modify from one problem to the next to fit your purposes, because in each problem you have a certain if you want bilinear or multilinear interaction structure that you're trying to capture, and you make your spaces fit the structure that you're trying to do estimates for. All right, so this is in terms of function spaces. And then the next interesting question is the question of constructing a parametrics. You can think of this problem as constructing a parametrics for this paradifferential operator, which is the constant coefficient wave equation plus the paradifferential part, or the question of proving estimates for the corresponding covariant wave equation. Okay, this is how the estimates should look like. And the key idea here is that what you'd like to say is that this covariant wave flow looks very much like the constant coefficient wave flow after a suitable renormalization. And this renormalization, in a nutshell, you can think of as some operator that will interchange the covariant wave equation with the constant coefficient wave equation up to perturbative errors. So you don't care about having an exact conjugation here, just something approximate. And this was a key idea of Tao in studying wave map equations, and this provided the second building block to understanding small solutions to wave maps. And again, this parametrics was further simplified and refined, including in work that I did, and then work that I did together with disturbance that I will mention in a bit. There is a second parametrics construction that occurs in the context of the Maxwell-Klein-Gordon equation, which was introduced by Rodniansky and Tao. So that's the counterpart of the wave map result of Tao, and the counterpart given by Disturbance and Krieger of this construction in the context of the Young-Mills equation. Initially, Tao's parametrics was in high dimension, then also in low dimension. These two parametrics here are in high dimensions, but they essentially carry out a conjugation exactly of this type. And maybe I wanted to, and I think I have a little bit of time, to tell you a little bit more about how this conjugation works. And in order to do this, I have to show you how these paradifferential equations essentially look like. So if I'm looking at wave maps, then you're looking at the equation box pk plus something that looks like a alpha d alpha pk is equal to 0. And the important thing to remember here is that phi k is a vector and a alphas are matrices. All right, these are at frequencies less than k. And the important feature of this matrices are that they have some conservation structure. In other words, these are anti-symmetric matrices. If you look at the corresponding problem for the Maxwell-Klein-Gordon equation, this will look actually simpler. So for mkg, your paradifferential equation will look again like box phi k plus, and here I'll put an I, a alpha less than k, phi k, let's say is equal to 0. This time phi k you think of as a complex valued function, and you think of a real valued electromagnetic potential. So this corresponds essentially to a commutative version of the non-commutative equation that you see in here. And finally, if you look at the Young-Mills equation, that goes a little bit more along the lines of wave maps. Your equation will look like box bk plus, and here you have a Lie bracket, A alpha with D alpha B is equal to 0. And now B takes values in your Lie algebra. And A also takes values in the Lie algebra. But the common feature between all of these three problems is that your magnetic potentials, so to speak, have this anti-symmetry property.
It's equal frequency less than K.
This is, yes, alpha A is at frequency less than K, and B is at frequency K. Maybe here, let me add the correct indices. Otherwise, somebody will get upset. All right, so write things in a nice covariant fashion. And so in each of these problems, looking at a good renormalization, let's say for the wave map equation, corresponds to choosing an orthogonal matrix O, so that essentially you need an equation which says that d alpha of O times O inverse is something like A alpha. I'm going to lower the index here. And if you do the same computation for the Yang-Mills equation, you get exactly the same relation. And if you do the same computation for the Maxwell-Klein-Gordon equation, then you're going to end up with a relation. You're going to think of your gauge transformation as a multiplication by some e to the power aib, and then your relation, the relation that you'd be looking at is d alpha of B is equal to A alpha, more or less. And so the question is if you can realize something like this. And of course, if you want to solve this equation directly, this is not a single equation, it's a system of equations over alpha. And they're all equations for the same unknown, so obviously you're going to have compatibility conditions. And these compatibility conditions would essentially tell you that the curvature of the connection determined by A has to be 0. And of course, the curvature is not 0, otherwise you would be solving the constant coefficient wave equation rather than a covariant wave equation. But what saves you in the case of the wave map equation is that this A alpha, even though they are not, they do not have curvature 0, they have a special structure, which is that A alpha looks like some, if you want, phi times d alpha of phi. So maybe to the leading order, the curvature of this expression is 0. And this is what allowed Tao to construct an approximate renormalization matrix O. So O here would play the role of an orthogonal matrix. In Tao's initial approach, O was not orthogonal, was only almost orthogonal. But for the large data problem, it turned out it's a lot more interesting to work with matrices which are exactly orthogonal. So this is really the story for the wave map equation. For the Yang-Mills equation, for the Maxwell-Klein-Gordon equation, on the other hand, this is a linear relation, and this magnetic coefficients A alpha are very far from having 0 curvature. So you might say, oh, solving this is hopeless, right? However, one key observation that Rodniansky and Tao made was that even though you cannot integrate an arbitrary electromagnetic potential over in all possible directions, you can always do the integration in one dimension. And so for each C, for each spatial frequency C, you can approximatively solve this. You can write essentially an equation that looks like psi alpha, if you want. Let me if I'm looking at the symbol of the nonlinearity over there, that alpha times B is equal to A alpha psi alpha. And if you do a division in here, what you're going to come up with is a symbol B, which will not no longer be a scalar function, and instead your symbol b will be a function of x and psi. So this is a pseudo differential operator. So instead of doing the conjugation as you do it in the case of wave maps with a scalar normalization matrix, here you are going to do the normalization in a pseudo differential, and if you want in a paradifferential style. And then the challenge becomes to understand what is the regularity of this symbol that you construct and set things up so that this symbol has as good a regularity as possible, and so on. Now, when you try to solve a similar problem for the Young-Mills equation, you are really going to face a superposition of the problem that you have for Maxwell-Klein-Gordon, which is that you need to look at the pseudo-differential operator, and of the problem that you have for wave maps, which is that you need to integrate in a nonlinear gauge theory, okay? So the solution for the Young-Mills, the way we eventually figured it out, is to apply these two algorithms successively. So here you apply the Maxwell-Klein-Gordon idea first, and then you apply the wave map method next, and then you can do something for Young-Mills. So that's in a nutshell what happens from this perspective of renormalizing this paradifferential equations. And so on this slide I put the three theorems that I wanted to tell you about. The first theorem is the one that was originally obtained by Terry Tao for the case when you're looking at wave maps where the target is the sphere, and then Joachim Krieger figured out how to do the hyperbolic space, and then I was able to look at arbitrary target manifolds with some, maybe some geometrical constraints. Maybe I should mention here that, so these are the results in two space dimensions, which is the energy critical problem. And independently, there are a few other works which provided simpler approaches in higher dimensions. Higher dimensions here are a little bit easier, and in particular I should mention the work of Sergiu together with Igor, who provided a very nice and elegant approach, I think in dimensions 5 and higher. The second result is the same result for Maxwell-Klein-Gordon, that for small data you have global well-posedness and scattering. That's what Rodniansky and Tao originally did in high dimensions, and then in low dimensions, this is the work that I did together with Krieger and Sterbens, and comparing with Joachim's talk, I think I got the year wrong. It was maybe 2012. And then the third theorem is more recent work that I did with Joachim, again in low dimension, which extended his original work together with Jacob Sterbens in dimension 6 and higher. So these three theorems address the small data problem in all of these situations. And one consequence, if you want, of this renormalization process that one goes through, and the fact that the nonlinearity is non-perturbative, is that this well-posedness results, even though there are well-posedness results for linear, for semi-equations that formally look like semi-linear wave equations, they are what I would call quasi-linear well-posedness results. In other words, you have existence of solutions, you have uniqueness of solutions, but what you do not have is you do not have Lipschitz dependence of the solutions on the initial data. All you can hope to get in this scale invariant setting is a continuous dependence of the solutions on the initial data. And so estimating differences of solutions is quite a non-trivial process, and you always can estimate differences of solutions only in lower topologies than the topology where you're solving the equation. And this is the same as if you're essentially as if you're doing well-posedness for a nonlinear wave equation. You see exactly the same phenomena. So keep in mind that you have quasi-linear well-posedness. And the other thing that you will see is that You do not have standard linear scattering. In other words, your solutions do not approach a solution to the linear wave equation at infinity. And the reason for that is that your underlying linear equation is the paradifferential wave equation, not the constant coefficient wave equations. So what you will approach at infinity is a solution to this paradifferential wave equation. Okay, so this is the small data problem, and now I want to turn my attention on the large data problem, and that's where it becomes more interesting to look not at all dimensions, but especially at the at the dimension where the problem is energy critical, in other words, where the energy is scale invariant. And so that's the two-dimensional problem for the wave map equation, and the four-dimensional problem for Maxwell, Klein-Gordon, and Young-Mills. Now, so here n represents the space dimension, and you also have time. And one obstruction, like Joachim described nicely in his talk, is that you have obstructions to global well-posedness, and these obstructions might be blow-up solutions, might be solitons, stationary solutions, and so on. So a natural threshold that emerges in this context is that of the ground state, where you look at all stationary solutions, and of them, you choose the one which has the lowest energy, and that's what we call the ground state, and our main reference here will be the energy of the ground state. And so the threshold conjecture, which would apply to all of these problems, states that whenever your energy is below this ground state energy, you expect to have global well-posedness and scattering. And again, the modified scattering that I was telling you before. In the absence of a ground state solution, you expect to have global well-posedness. All right? And now a lot of more interesting phenomena happen if you are above the ground state energy. Joachim talked about that, and I'm not going to say to add anything in that direction. So the question, the results that I want to tell you about address this threshold conjecture for these problems. And as many of you know, I'll mention three methods of studying these problems, and their common goal is the same, which is to say that whenever your energy, the energy of your solution is below the ground state, then you have an estimate which measures your solution, which I'll generically call by phi, in a good, if you want, null frame space, in terms of, as a function of the energy of your initial data. And the first such method historically is Bourgain's method, which is provides a direct induction on energy, which is great when it works, but it's always difficult to implement, because if you want it, it mixes the perturbative and non-perturbative parts of the argument in a single big whole, and so that makes for proofs which are very involved technically. And one key simplification of this was the method of Koenig and Merle, where you divide and conquer. You split your problem into two parts. First, you want to show that if such an estimate does not hold, then you have what is called the minimal energy blow-up solution, which has this very nice compactness properties that, again, Joachim very nicely described. And then the second part is to disprove the existence of such a minimal energy blow-up solution. And this method has indeed led to much simpler proofs to some of the, even some of the classical results in semi-linear wave equations. And particularly it's led to simpler proofs in anything that's related to nonlinear Schrödinger equation. And finally, the third method, which is the one that I will tell you about, is what we call the energy dispersion method. This is a method that was introduced in work that I did together with Jacob Sturbens, which again is the same strategy to divide and conquer, except that you draw the line in a different place. And to our mind, this is the method that works best when you look at gauge theories. So our method would not give you anything brilliant if you look at the semi-linear wave equation or at the semi-linear Schrodinger equation. But if you look at the problem where you require renormalization, in other words, a problem where you have non-trivial interactions between low frequencies and high frequencies, to my mind, this method provides a better way to victory. So it relies on this concept of energy dispersion, which measures how much your solutions are concentrated in a point-wise manner, which is the obvious thing that you should look for. And so it still has two steps. One, that energy dispersed solutions are global and scatter, and this is sort of the perturbative part of the argument. And then, once you know that these guys are good, you want to establish a dichotomy. Show that this energy any solution either has energy dispersion or has pockets of energy that give you steady state. In other words, that give you at least that minimal ground state energy in the limit. Okay, so this, you can think of this as an alternative of the Koenig-Merle method, which applies to these gauged problems. Now, Joachim also told you about his work with Jacob Luhrmann, where they implement this, and then his prior work, I should say, with Wilhelm Schlag, where they try to implement this Koenig-Merle method for gauge wave equations. But in my talk, I will emphasize this second method, the energy dispersion method. So before I tell you more about these methods, let me tell you about the three results that I wanted to mention. First is a result with Jacob Sterbens on wave maps, where this threshold conjecture is established. And this result was paralleled by work of Krieger and Schlag and Tao in special cases where the target manifold is the hyperbolic space. The difference somehow is that when you look at the hyperbolic space target, you do not have ground state, so you always have global solutions, whereas for arbitrary compact manifolds, you will always have, most often have ground states, so you have to worry about the real threshold occurring in the problem. The second theorem is work that I did with Sungjin Oh, and work that independently was done by Krieger and Luhrmann, and that's for the Maxwell-Klein-Gordon equation in 4 space dimensions. And one feature of the Maxwell-Klein-Gordon equation is that here you do not have a ground state, which means that you expect to have global solutions for arbitrarily large data. And the last theorem, this is not finished, this is joint work with Sungjin Oh. It's work in progress, where we're working on proving the same result for the Young-Mills equation. Maybe one difference between what we did before on the Maxwell-Klein-Gordon equation and the Young-Mills equation is that the Coulomb gauge, which I mentioned before, the gauge choice is important in these problems, to our mind no longer seems to work for the Young-Mills equation. So for the purpose of the Young-Mills equation, we are switching to the caloric gauge, which is very dear to my collaborator Sungjin, because that was part of the subject of his PhD thesis with Sergiu. As I said before, one can attempt to prove this either by using concentration compactness, the Koenig-Merle method, and the energy dispersion, and I will discuss this method of using energy dispersion. And in none of these problems, in neither of these problems, you have to worry about a blow-up, a similar blow-up scenario, which seems to occur more in supercritical problems. Okay, so Next, I'll try to explain to you what this method of energy dispersion is. So, a priori, when you look at, let me specialize this discussion to the wave map equation, where you're looking at solutions, let's say phi, which belong to where the initial data is in the space H1 of R2, right? And you all know that by Sobolev embeddings, this does not embed into L infinity, but it does embed into BMO. However, if you take the dyadic part of an H1 function that is in L infinity, and that explains this norm that I'm putting in here, where I take each dyadic portion of my map phi, and I'm measuring this in L infinity, and now I'm not trying to add this in any way, and instead I'm adding those with, I'm taking the supremum of those with respect to k, where k represents a dyadic frequency index. So k is goes over the integers here. And so this energy dispersion norm is, first of all, scale invariant, has the same scale as the H1 norm in here, which is the same scaling as the energy. But instead of measuring concentration, if you want, in some H1 fashion, measures the concentration in a pointwise fashion. So it's much easier to concentrate, if you're on the H1 norm, than to concentrate than to have this energy dispersed norm large. And naively, the reason for that is whenever you have nonlinear interactions, those nonlinear interactions are worse when your functions are pointwise large, not just large in an integrable sense. So you're looking at points in the space-time where your solutions have large pointwise size, and that's what this measures. And the second comment that I should make in here is that when you're measuring this norm, you're not measuring this norm for the initial data. You're measuring this norm for the entire solution, right? Because you might very well have solutions for the wave equation where at the initial time your solution is quite dispersed, but maybe it concentrates on a sphere, and then maybe at some later time you're going to see concentration occurring. So then you want to measure this concentration here, not here. And that explains my comment in here. And the theorem that applies in all of these three problems tells you the following. Tells you that once you fix the energy of your solution, then there exists a threshold for this energy dispersion, so that below this threshold, if your energy dispersion is sufficiently small, and this is in a way that depends only on the energy, then you have a good control over the S norm of the solution. In other words, you have everything that you could possibly want in terms of estimates for your solution. So if your solution doesn't concentrate at any single point enough, then your solution is essentially driven by a linear by perturbed linear dynamics. That's a naive way to think about this. And so I wanted to tell you a few words about the proof of this theorem with a drawing. And I'll do that drawing in a moment, but first I'll switch to the next slide. So the key element of this proof is that this proof is an induction on energy. So this is in the, if you want, Bourgain style, where, let's say, if I'm putting the energy on this line, let's say I know that my theorem holds up to some energy E, and I want to show that I can push the result to an energy E plus C, and eventually that this way I capture all possible energies. Now, the important step in an induction on energy argument is that you should be able to go all the way to infinity in here, which means that the increment, the C that you see in here, must depend only on the energy E, right? The C you cannot afford your C to depend on epsilon of V or on F of V that you see in here. So C should depend only on the energy E. All right? And so now what you do is you take here some solution phi that has energy dispersion, and which has energy E plus C. Okay, and so what you want to do is you want to reduce the study of this solution to a solution with a smaller energy, with the energy E. And you do this by a naive truncation in frequency, to which maybe you make some nonlinear adjustment if your state space is not a linear space. So I have my original solution, my original data phi. I have a perturbed data, which is maybe, let's call this phi tilde, which has data phi restricted to some lower range of frequency with a cutoff frequency k star, which depends on phi. Now, for this function phi, you have energy dispersion, all right? And so what you would hope to show is that this energy dispersion translates to this solution which has only energy E. Now for the solution with energy E, you want to apply your induction hypothesis. All right, and if you apply your induction hypothesis, then you're going to control a norm of phi tilde in S. And now, if you control phi tilde in S and you are able to prove that phi and phi tilde are sufficiently close, then this would allow you to control norm of phi in S. The difficulty in this argument is that when you do this step in here, you're also using this piece of information. And this makes this in a beautiful circular argument. We do not like circular arguments. So you have to be very careful of how you introduce successively your constants in here. And the bottom line here is that this epsilon, you can make it arbitrarily small. And so in other words, in all of this argument, whatever depends on epsilon is a clear win. Now, in order to be able to carry out this argument that, as I drew it, looks circular, you have a couple of interesting points to cover. First of all, in all of your bilinear and multilinear estimates, you'd like to use the energy dispersion to have gains, all right? And unfortunately, this doesn't work. You are only going to see this gains in bilinear estimates when you have balanced frequency interactions, where you have two waves of approximately the same frequency that interact. Then energy dispersion gives you a big gain. But if you are looking at two frequencies which are very unbalanced, very low frequency, very high frequency, there the energy dispersion doesn't help you. And in this bilinear analysis, a key role is played by the bilinear Strickhartz estimates of Wolf and then Terry-Tao. Okay, so this is one step. But of course, when you look at these gauge problems, the non-perturbative part of the nonlinearity contains exactly the interaction of low frequencies and high frequencies. So whenever you're looking at this term over here, this term will never improve because of this energy dispersion. So what do you do with that term? You need a second proxy for smallness. And this second proxy for smallness is what we call the frequency gap, M. In other words, when we look at this gauge coefficient in here, we don't allow this coefficient to be at frequencies all the way to frequency k, but instead we separate the frequency of the coefficients in here by the frequency of the function we're trying to estimate by this large parameter M. And this large parameter M, if you can make it large enough compared to the S norm of this coefficient's phi that you see in here, then it acts as a proxy for smallness. Then you can get some smallness out of this frequency gap. So here you don't use any energy dispersion, and sort of another advantage that you get out of this is that your proof will be more modular. This part 2 is completely separate from part 1 above. These two steps still do not finish the proof because they do not guarantee that the proof is not circular. And in order to guarantee that this proof is not circular, you need this additional property, which is what we call divisibility estimate. And the point here is the following. If I have a function, let's say phi, in some LP space, where p is not infinity, then I can divide my time interval into small pieces and make all of those norms small in each of this time interval. I might have many time intervals, but in each of those time intervals, the norm will be small. Now, in our case, what we have to work with is this norm S. Okay, and this norm S in particular contains a lot of stuff in it, but in particular, it contains energy type norms, which is L infinity, L2, L infinity in T, L2 in X. So no matter how much you chop your time interval, you're never going to be able to make such a norm small, right? So it looks like in this space S, you do not have a divisibility property, and that's a serious problem. However, what does work, and what turns out to be sufficient for all of these problems, is that you can split your time interval into pieces so that each piece is not arbitrarily small, but you can make it comparable to the energy. And everything that depends only on the energy is a win here, because what you're trying to aim for is an increase in energy C, which depends only on the energy, all right? And so, furthermore, any norm of this type, L infinity L2, is an energy norm. So this is controlled by the energy. So when you divide, these norms don't cause a problem. These are already controlled by energy. And so this is how this divisibility estimate works, and this is the final nail in order to prove this, in order to conclude this induction on energy proof of this energy dispersion theorem. All right, and the last step of all of these proofs of the large data results, as I was saying, have to do with establishing a dichotomy. You want to say that for an arbitrary solution, you have either energy dispersion or you have some sort of soliton-like concentration. And the picture that you should keep in mind here is the following. From the perspective of the non-blow-up, of eliminating blow-up, you're looking at, because of the finite speed of propagation, you're looking at solutions which live in a light cone, and what you would like to be able to say is that as you approach the tip of the cone, the energy of these solutions decays to zero, so that you can fall back onto the small data problem. And the second situation that you want to look at in terms of scattering is you're looking at solutions that move forward in a cone, and you want to be able to say that as you approach infinity in this direction, your solution has this energy dispersion property so that it looks like a linear solution, like a perturbative solution to your covariant equation. All right, and so this business with the concentrations, I can put it on this picture in the following way. So you're going to have a sequence of points, which in this case approach the tip of the cone, and in this case run to infinity. And around this point you have a corresponding sequence of scales, all right? So that when you take each of these pictures and you blow them up to the unit scale, or you reduce them from here down to the unit scale, in the limit here you're going to get a soliton. And the soliton has to have at least as much energy as the ground state, and therein lies your contradiction. Now, the important thing when you look at this picture here is that these points, together with their corresponding balls, stay strictly inside this cone. They never approach the boundary of the cone. And this explains some of the steps that you have to undertake in here. The first step is the absolutely straightforward one, where you write down the energy flux relation. In other words, you look at energies on slices here, and then you look at the flux on the lateral boundary of the cone, and what you want to say is that your energy on slices decays as you approach at the tip of the cone, and at the same time your flux on the lateral boundary, which is the energy that escapes, goes to 0. The second step in here, which is based on Moravec's identity with this vector field, and this plays the same role as some of the vector fields that Joachim showed in his talk, is one role of this is to eliminate the null concentration scenario. So what you would like to say is that there's no action happening near the boundary of the cone. You cannot have these pockets of energy very close to the boundary of the cone, and you eliminate those using Moravec's identities with this vector field. And so once you have eliminated this, then you know that you're going to have, at various points, a lot of energy strictly inside the cone. Once you have a lot of energy strictly inside the cone, and you know that your flux is very small, so nothing goes out, then you can show that this concentration of energy persists inside the cone. That's the next step. And finally, the last step in this proof, which involves a bunch of pigeonhole type arguments, is that you're looking at this, all of these solutions where you have enough concentration inside the cone, you rescale them, you put them all on the same scale, and so you use pigeonhole arguments to extract by some compactness argument a limit of this, and this limit has to be either a self-similar solution or a soliton. And then you exclude self-similar solutions by general principles, and you exclude solitons because your energy is below the threshold energy. All right, and so this is how this argument works. I know that I was pretty brief, putting maybe something like 50 pages of mathematics in a single slide, but what I tried to outline for you were the ideas of this results, and if you're curious, you can go to the papers. So again, I want to say thank you for inviting me here. I'm very happy to be here on, even if it's not Sergiu's birthday, on Sergiu's birthday. And happy birthday.
Are there questions?
So what's left?
Well, maybe some of the most important questions that are left were outlined by Joachim, which are to look at data which is large, which is above this ground state energy, and to prove the soliton resolution conjecture in this energy critical problems. Obviously, the next interesting step is to gain a good understanding of supercritical problems, of which we're still far from.
You have mentioned two instructions to get this large data existence. So the first one was the static solution, and the other one was the blow-up solution. If you remove the possibility of having blow-up solutions, would you be able to prove something?
Well, I added the blow-up solution obstruction in these problems as a matter of general principle. But the fact is, in neither of these problems, you cannot have self-similar blow-up solutions. So really the only enemy in these geometric equations, at least when you look at them in the energy critical case, you only worry about stationary solutions and their Lorentz transforms. However, if you try to look at problems in higher dimensions, not in the energy critical dimension, that's where you will encounter this self-similar obstructions, which create, as Joachim explained, new thresholds, if you want, for the small data theory. Though it's not so clear how you can measure those thresholds lacking an energy, a clear energy that is conserved.
If not, let's end.